questions. So Jonas, thanks very much also from my side. It's my honor to introduce the last speaker of our session, my colleague and friend, Robin Schubert. Many of you have used the Q-motor systems in multiple trials, and he's been your trainer, I'm pretty sure. So he's known to many people, and he's going to talk about his baby today. Whenever I told you about results in the past years, they were usually processed by Robin. So he's the brain behind it all with the group that's present here somewhere. So Robin, please go ahead. You'll give us your vision.
Thank you, Ralf, for the nice introduction. Yeah. And I'm super excited to be here and to speak here and to tell you about the lessons that I have learned with the Q-motor in the last couple of years. So, in case you wonder who's that guy anyway, and what does a physicist do in Huntington's? That's a question that I'm asked sometimes, and to give a job description is rather difficult to do. And it also depends on who's asking, but I think that Q-motor guy is really the most appropriate job description that I can give. And yeah, this is a picture of a 10 years younger me the day that I walked into the University Hospital in Münster to start my journey in Huntington's disease. And a couple of things have changed since then. For one thing that I'm particularly grateful is that I'm not the only Q-motor guy anymore. So there's Benjamin Hubble, or biomedical engineer, and Pascal Barallon, or mathematician. And of course, there's Ralf. And together, we are the Q-motor team working as Quantimedes. This is the company of GHI that we founded also almost 10 years ago, and by now been even moved out of the University Hospital and into our own building, still in Münster, Germany, however, because it's beautiful there. And of course, I have to start with what is Q-motor when I want to tell you about the lessons learned with Q-motor. And I remember when I walked into the lab, and I saw this device, I said, oh, what is that? And the answer was, oh, that is Q-motor. And I thought, okay, now I know what Q-motor is, but it took me some time to realize what Q-motor really implies, and I tried to display that in a comprehensive way. So, of course, we have hardware. We use force sensor and a position tracking system that we ship together with laptops and also custom-built devices to the sites. We have software to operate that hardware, to do the analysis, to do the data processing and whatever. And by now we even develop and maintain all the software that we use by ourselves. We have the assessments, of course, so the Q-motor assessment battery, which also includes the speeded tappings, very similar to what Jonas just presented, where you do tap your index finger on the force transducer as fast as possible. I don't have time to go into much detail on the rest of the assessment battery. The Q-Cog I will say some things about briefly later. And then we have Q-motor as a service. So, of course, those devices have to be shipped to the sites and back, and we have to write specifications, documentation, have to train the staff on site. And if you have Q-motor in your study, then you always get this full package. So, what did we learn about the placebo effect with the Q-motor? I had to build myself this reminder here. So RDBPCCT, what that means is it's the randomized, double-blind, placebo-controlled clinical trial. And I make it short because you will know what that means. We have a participant group that we want to treat with a drug or therapy, and we have a control group to make sure we can see there's an effect that is not there in a group that we do not treat. And to make sure nobody is cheating intentionally or unintentionally, we give that control group a placebo or sometimes even a sham surgery, and we do not tell the participants nor the physicians who belongs to which group. So we are placebo-controlled, double-blind. And yeah, we did a study with AFQ-056. That's a drug that was meant to reduce chorea in Huntington's disease, was also tested in Parkinson's disease. And when we looked at the UHDRS total motor scores at the end of the study, then you can see the line, the solid black line here. This is the group treated with AFQ-056, and you see that they are going down in their total motor scores, means showing less motor symptoms, which is good. Bad thing is that our placebo group just shows the same behavior. So yeah, that's the placebo effect. Fine. We knew that this could happen. That's why we have a placebo group at all. But then we looked at Q-motor data. And Q-motor data that I show in this presentation, I only show this the tapping speed in the speeded tapping task. And looking at the Q-motor data, we can see that, again, the solid black line, the AFQ056 group indeed was tapping faster while they were treated with the drug. And on the baseline, you can see that the placebo group just stays flat on the baseline. So we did not see this placebo effect in this data. And that was exciting, and with that experience, we went into the PRIDE HD study, way bigger study, over 50 sites with more than 400 patients, participants worldwide, and this time with 4 treatment groups and 1 placebo group, and looking at the Q-motor, total motor scores, again, we can see that we have a huge placebo effect. Every group is getting better, showing less motor symptoms in the total motor score. Looking at the Q-motor data, again, the tapping speed from the speeded tapping task, we can see that, mind the scales, this is inverted in this figure, that the treated groups were indeed tapping faster, and the placebo group just showed deterioration, just were tapping slower in the course of the 1 year of this study, which is what we expected. This is why we do the speeded tapping anyway, because we know that people with Huntington's disease tend to tap slower while the disease progresses. So again, no placebo effect in this study. And we did the same thing in a study with Ipsen, a very small phase 1 study, only 10 participants per group, in this case 3 groups, 1 placebo group and 2 cohorts treated with the medication. And again, the UHDRS total motor score suggests that the placebo group is much better, indeed it tends to be better than the 2 treated groups. And looking at the Q-motor, then indeed the placebo group does not show any difference from baseline, but the treated groups showed slower tapping. So in this case, we were measuring a negative effect on the drug in a very small cohort, so also that was possible with the absence of any placebo effect visible in the Q-motor data. I make it short, we saw the same thing in the Legato HD trial, huge placebo effect in the total motor scores, not visible in the Q-motor data, but indeed deterioration on the placebo group and a positive effect on the treated groups. We saw the same thing in the Amaryllis study. There was one special thing here. We even saw dose-dependent effects and also effects that we could reproduce in the open label phase of the study. So when even everyone, the physicians and participants, knew that they were taking the highest dosage group of the drug. Yeah, so that's what we learned about the placebo effect. I cannot tell you what drives the placebo effect, but we learned that we do not see it in Q-motor data. Yeah, this slide. This is Usain Bolt, the guy in the middle. For those who don't know him, he's a very fast runner. And these are his fastest times in 12 years on 100 meters. And I'm showing you this because what we ask from our participants is to give their best performance every time they come into the clinic. And just like with Usain Bolt, also the participants, when we look at the individual data, we will always see ups and downs. And I just show this because I want you to remind that the data that I showed are results from statistical models. We still need the statistics to reveal those effects because the statistical models also take more into account than just Q-motor data. They have sex and age and CAG repeats and of course also the treatment groups. So yeah, just to keep that in mind. And that brings me to the next point, similar to what Jonas just said. How can we push the effect even further? And that's the center of my personal research, just looking at the time. Also where we introduced the Q-Cog, a cognitive assessment battery for the Q-motor. And I will not go into detail on all the tests, but rather want to present the means that, or the approaches that we use to increase the effect that we see. One of this is to adjust the difficulty. So this is an example for the force matching task that we do. In the force matching task, you have a line on the screen presented to the participant, and it stands for a force level. And you see also a symbol that you can move up and down by applying force on the force transducer. And the task is to match the symbol with the target force level on the screen. And of course, having a task like that, you can make it arbitrarily complex and more difficult. So we can adjust in the trial also for the participant groups we have in the trial. At least that's the goal. And I also have a poster on that in the exhibition area. Come and find me there if you want to learn more about the force matching. Another task or another approach to increase the effect that we see is to translate tasks that are already working for the clinic, like pen and paper tasks. We have this 3D tracking pen that we can attach to our 3D tracking system and that we modified so it can actually write. And there's, for instance, a group in Tübingen that does the trail making test, the spiral drawing test that I also have a poster on in the exhibition area. And the trail making test, which is also very popular in Huntington's disease, because it's already sensitive for cognition in Huntington's by just having the output time to complete the test and numbers of errors being made. So just as a reminder, the test is to connect the dots from 1 to 2 to 3 and so forth. So doing that digitally will just give you a bunch of more information all of a sudden by doing the same test. And all of a sudden you can look at velocity profiles and acceleration profiles, and you can go into Fourier space and analyze the spectral arc length and things like that. So the idea is to get more data from the same test. And the last approach that I want to show you is the dual tasking concept that you probably also know already. So you let the participant learn 2 separate tasks, and in the dual tasking paradigm, you let them do both tasks simultaneously. And that is a cognitive challenge because the tasks will just battle for the cognition in the patient. And in this case, we did the speeded tapping with the left hand and a lateral pointing movement in a pre-specified order on the table with the right hand, and let the participants do both simultaneously. Very interesting results. It was just a proof of concept study, but I also have a poster on that one if you want to have more information here. Okay, so finally, I want to share my personal lessons that I have learned coming from as a physicist into clinical trials. And I tried to make that visible with this very simplified figure. So the idea is you have multiple players in a clinical trial. You have the participants, the investigator sites, you have the vendors and the CROs, and of course the sponsor. And I believe that if we manage to make all those people more happy, then they will be more committed to the trial and they will deliver better data, which in turn will people make more happy. Just as an example, take the participants. If we give them tasks that are just so exhausting that they at some time will stop doing them, not do them correctly, or simply drop off the study, then this is no good for the study. If you have if you have things that are so complex that it's very difficult to integrate in the clinical all-day routines of an investigator site, then these things will also tend to be forgotten or not done correctly. And I don't have time to go into all the groups, but you get the idea, I guess. So maybe to summarize what I have learned in general about clinical trials is that we need assessments that are objective and unbiased, robust, sensitive, and easy to use, which is easily said, but of course hard to design, I know. Also, we need trial designs that make sure that we collect the data that we need, but not more, because again, that will just put more burden on the participants, on the clinical study sites, on everyone. We need the clinical study sites. That's one point that I'm particularly fond of. For me, the clinical study sites are the only interface that I have to the participants. I can talk to anyone else in the study, but not to the participants, and I probably should not because no one knows them so well like the investigator sites. So feedback that I can get from clinical sites is invaluable for me. It's the most valuable feedback. And also, I can assist remotely if clinical sites have a problem, but what I cannot do is to hold a screwdriver remotely, and we have that situation. We had it a couple of times where that was necessary. I'm really grateful for all the study nurses that helped me out in situations like that. And I think they do it because they are committed to the trial and they want to record good data. Yeah, so I guess the bottom line is we should try and make it possible to keep the motivation high and the burden low of everyone involved in clinical trials. Thanks, I guess that's everything from my end.